Hi, my name is Tim Triple, and I'm a PhD candidate at the University of Michigan. Today, I'm going to tell you about a technique we developed to vet untrusted third-party hardware IP for ticking time bomb Trojans. This is joint work with Kong Chen, Kevin Bush, and Matthew Hicks. Hardware is the foundation of all computing systems, from laptops and cloud servers, IoT devices, portable electronics, and automated retail spaces, to more mission-critical systems like network infrastructure, medical devices, autonomous vehicles, and drones. All computing systems share one thing in common. They all blindly trust integrated circuit hardware to reliably behave according to specification. Over the last 15 years, computer architects have increased the amount of on-chip parallelism to overcome performance barriers due to fundamental physical limits. And while this parallelism started off homogeneous in nature by increasing the number of logical cores, it has become heterogeneous over time as domain-specific accelerators have become commonplace. Unfortunately, with increased parallelism comes increased complexity. Take the recently released Apple M1 SoC, for example, that has over 24 different categories of IP blocks on board. If we look closely, we see the M1 SoC contains both general purpose processors, cores, such as CPUs and GPUs, to domain-specific accelerators, such as cryptographic accelerators, machine learning accelerators, image processing accelerators, and many others. In order to minimize time to market while maintaining feature-rich designs, most semiconductor companies outsource portions of the design process by purchasing third-party IP to include in their designs. Outsourcing, combined with the complexity and scale of integrated circuit hardware, presents a security risk. How do we know untrusted third parties will not include a backdoor or hardware Trojan in their designs? There has been significant prior work to address the issue of untrusted or outsourced third-party IP, shown here. These techniques have consisted of both static and dynamic analyses that share one thing in common. They are too extreme. That is, they either attempt to be Trojan agnostic or implementation specific. Unfortunately, researchers have continued to demonstrate false negatives or Trojan designs that bypass these defenses. Rather than continue to build defenses at these extremes, we argue for a divide and conquer approach that fills this trade space, namely creating defenses that systematically define and search for specific classes of Trojans based on their behavior, not implementation. And we demonstrate the effectiveness of this approach by first targeting ticking time bomb Trojans. So what are ticking time bomb Trojans, or TTTs, and why do we want to start by eliminating them? There are many different ways to categorize hardware Trojans, the first being where in the hardware design process they are inserted. Our focus is on eradicating malicious hardware inserted during RTL design as a result of outsourcing this process to untrusted third parties. Design time hardware Trojans can further be classified based on the characteristics of their two main components, their trigger and payload. The trigger is the portion of the Trojan that hides the Trojan's payload until a specific state is reached or condition is observed. It enables the Trojan to remain dormant under normal chip operation. Alternatively, the payload is the portion of the Trojan that manipulates the victim circuit upon being signaled by the Trojan. Since the payload is usually specific to the victim circuit where the Trojan is implanted, we choose to further classify Trojans based on their trigger, for which there are two types, always on and initially dormant. Since always on triggers are often easily detected during verification testing, since they lack any triggering mechanism at all, we focus on the most stealthy Trojan triggers, those that are initially dormant. Lastly, there are two main categories of initially dormant triggers: data-based or cheat code, and time-based or ticking time bombs. Data-based triggers are comprised of combinational or sequential logic that waits for a specific value or sequence of values to be expressed by signals or registers within the design. Alternatively, ticking time bombs or time-based triggers monotonically approach activation the longer the victim circuit operates continuously since the last system reset. As a first step towards systematically constricting the design time Trojan attack space, we choose to target ticking time bombs, as prior work has pointed out that they, one, require little additional logic or components to implement, And two, they do not require any attacker post-deployment interaction, since they start working towards activation the moment the chip has been turned on. Therefore, eliminating TTTs forces attackers to implement larger Trojans that require post-deployment attacker interaction, thus raising the bar for the attacker. We start by defining TTTs as Trojans that implement ticking time bomb triggers, as shown in the upper right figure here. And we define ticking time bomb triggers as monotonically increasing counters that express values that 1, never repeat, and 2, never complete. This is because if a counter repeats a value, it is no longer always monotonically progressing in any direction, and therefore cannot implement a TTT. And if a counter enumerates all possible values and the victim circuit does not exhibit abnormal behavior, then it is also not part of a TTT. From this succinct definition, we enumerate the space of all possible TTT designs, including some novel variants, based on the 3 fundamental components required to implement this type of behavior in hardware. These components include 1, state-saving components, or SSCs, which store the counter's current count. 2, an increment event, which triggers the counter to increment its value. And 3, an increment amount, which determines the next value in the counter sequence. Since each of these components can be implemented in different ways, the TTT design space we define is more general than it first appears. Specifically, SSCs can be broken into 2 variants, coalesced and distributed. An example of a coalesced SSC is a contiguous 4-bit register. Alternatively, rather than use a single contiguous register to store the count, a savvy attacker may choose to combine multiple smaller SSCs into a larger distributed SSC, as shown on the right. Increment events can be either periodic, for example, a clock signal, or sporadic, for example, an interrupt signal. And increment amounts can be uniform, for example, incrementing by 1s or 2s, or non-uniform, for example, incrementing by the last 4 bits of the program counter. What is cool about our definition is that regardless of the type of components used to implement the counter, that is SSC, increment event, or amount types, all we have to monitor are the values expressed by the SSCs themselves. Putting it together, 2 simple invariants constraining the sequences expressed by SSCs define an entire space of TTT designs shown here. Specifically, in green, we note some unique TTTs our definition exposes. Our goal in this work is simple. Create a technique that can detect TTTs by their SSCs. Where prior work was trying to detect the entire trigger to find Trojans, by narrowing the scope to TTTs, we only need to monitor the behavior of SSCs. How does it work? Well, we first start by enumerating all SSCs in the design. While coalesced SSCs are simple, we just look for registers. Distributed SSCs are more complicated. We must search for all possible connections between coalesced SSCs. While this may seem computationally infeasible, since in the worst case the set of distributed SSCs would be defined by the power set of all coalesced SSCs, in practice it's actually not. The circuit itself constrains this set size since every register is typically not directly connected to every other register in the design. Once we have a list of all SSCs, we initially assume that they are all suspicious, or part of a TTT. Then we simulate the design using traditional verification test vectors. And lastly, we analyze the verification results and check if each SSC violates either TTT invariant at any time during simulation. If they do, then the SSC is benign and cannot be part of a TTT. If they do not, then the SSC could be part of a TTT and must be analyzed manually by a hardware design engineer. A key insight from our approach is that false negatives are impossible, since we initially assume all SSCs are suspicious and only mark them benign when we know for certain they are not. That is, they violate the definition of a TTT. We implement this approach in a tool we call Bomberman, the architecture of which is shown here. In the interest of time, I'm not going to go into the details of its implementation. However, if you are curious, please refer to our paper. Now that we understand how Bomberman works, the next question we ask is how effective is Bomberman in practice? Recall, false negatives are impossible given the construction of the Bomberman algorithm. However, false positives are not. So what is Bomberman's false positive rate in practice? Secondly, how does Bomberman stack up against prior work in terms of A, the ability to detect all TTT variants we define, and B, performance or runtime. To answer these questions, we study 4 real-world hardware designs, including a cryptographic accelerator, a UART module, and 2 CPUs. We implant all 6 TTT variants, the 4 coalesced and 2 distributed, in all of these designs and measure Bomberman's performance. To get an idea of the complexity of these designs in terms of number of SSCs, we plot the size and number of all coalesced SSCs or registers in each design shown here. While the paper details the results from all cores, in the interest of time, I'm only going to talk about the AES core as we believe these are the most interesting results. To study the AES design, we developed a simple test bench that drives random plain text and random keys generated by linear feedback shift registers into the design under test to be encrypted and the results verified. We choose this constrained random verification approach as it is representative of a real-world verification strategy. The AES design we study operates in 128-bit counter mode and has a delay of 22 clock cycles per encryption. Here we plot 4 traces that show the number of SSCs Bomberman identifies as suspicious over the course of a simulation that performs 150 encryptions. In blue and orange, we plot the number of suspicious SSCs reported for coalesced and distributed SSCs respectively. And in green and red, we plot the number of constant SSCs reported. A constant SSC is simply an SSC that has only expressed a single value since reset. That is, it has not progressed out of its reset state. Note, suspicious and constant SSCs are not mutually exclusive, since a constant SSC is, by definition, also suspicious. In the first half of this plot, we observe Bomberman's results over the course of encrypting 75 random plaintext with 75 random keys. We see that after approximately 750 clock cycles, the reduction in false positives starts to level up. This is because at this point in the simulation, Bomberman has observed all small SSCs cycle through all possible values. At this point, we recognize that it is infeasible for Bomberman to observe the same for large SSCs in any reasonable amount of time. To overcome this, we make another observation that since the AES core is a deterministic state machine with no control path SSCs, repeating input test vectors will cause all deterministic data path only SSCs to repeat values, violating the other TTT invariant of no repeated values. We demonstrate this idea by repeating the same 75 encryptions in the second half of our simulation. As you can see, shortly into the second half of the simulation, we eradicate all false positives and are left with only those malicious SSCs we implanted into the AES design to begin with. Overall, across all designs we study, we observe a false positive rate of only 1.2%. Now, if we compare Bomberman to other defenses in this space, we see it is the only defense capable of detecting all TTTs we enumerate in our definition. Moreover, in our paper, we demonstrate a TTT that can defeat all of these defenses combined, except Bomberman. While it may seem that the defenses like Fancy and Veritrust are futile, I would argue that they are not. Rather, they are very useful in a layered security manner, since the runtime for all of these approaches, including the Bomberman approach, are very low as well. Remember that while they may not completely defeat all TTTs we define, they can defeat some database Trojans that Bomberman cannot. In conclusion, Bomberman demonstrates the power of class-specific Trojan verification by eliminating the threat of TTTs. Moreover, its fast runtime enables defense in depth strategies where several defensive measures are deployed in unison. Lastly, its low false positive rate makes manual inspection of the remaining suspicious SSCs feasible. So where do we go from here? While the false positive rate is low, could we get it even lower? We made an observation with the AES core that it is feasible to trigger deterministic data path SSCs to repeat values by repeating test vectors. Is it also possible to repeat a sequence of test vectors to trigger repeated values in control path SSCs? And if so, could we automate this? If you enjoyed this talk and want to experiment with Trojan verification, please feel free to check out our source code at the link below. Thank you for listening to my talk, and if you have any questions, don't hesitate to reach out to me via email or during the live question and answer session.